When a ray of light from air enters a slab of glass, it is found to deviate. The angle of refraction is less than the incident angle. The difference between the angle of incidence and the angle of refraction is the angle of deviation. When light moves from a rarer medium to a denser medium, for example, from air to glass, the angle of refraction is less than the angle of incidence. The only exception is when the angle of incidence is 0 degrees, in which case the angle of refraction is also 0 degrees. When light moves from a denser medium to a rarer medium, for example, from glass to air, the angle of refraction is more than the angle of incidence. The only exception is when the angle of incidence is 0 degrees, in which case the angle of refraction is also 0 degrees. The cause of refraction is the change in the speed of light due to the change in medium. Light travels faster in air and upon coming into contact with glass slows down. This causes a change in the direction. When you use the slider to change the angle of incidence, you will find that the angle of refraction also changes. But in each case, if you take the ratio of the sine of the angle of incidence to the sine of the angle of refraction, it turns out to be a constant. This is called the refractive index and is constant for a medium with respect to another medium. The refractive index of glass with respect to air is approximately 1.5. If the refractive index of the glass was 1, then the light ray would have traveled from air to glass without deviation. If the refractive index was increased, the deviation would be noticed. As the refractive index is increased further, the deviation will increase. As the refractive index is increased, the angle of refraction decreases. When light enters a block, it deviates towards the normal. Then it travels through the block and exits again by deviating away from the normal. The ray of light entering the block is parallel to the ray of light emerging from the block. Lateral displacement is the distance between the lines entering and leaving the rectangular block. As the refractive index is increased, the deviation also increases, due to which the lateral displacement increases. In a prism, since the two refracting sides are not parallel, the incident and emerging rays are not parallel. If you trace the incident ray into the prism, as shown by the dotted line here, then the angle between that and the emergent ray is the angle of deviation. The angle A is called the angle of the prism. As shown, the two refracting angles are marked R1 and R2. If you take the sum of R1 and R2, it would add up to the angle of the prism, which is A. You can try by changing the angle of incidence to different values. In each case, R1 plus R2 will equal to A. This is another interesting rule in a prism. If you add the angle of incidence and the angle of emergence, you will find that its total always equals the sum of the angle of the prism and the angle of deviation. You can try changing the values of the angle of incidence and check if it follows the rule. As the angle of incidence keeps increasing, the angle of deviation keeps reducing. It reduces to a minimum value before it starts increasing as the angle of incidence increases. As the refractive index increases, the angle of refraction decreases. Due to this, the angle of deviation between the incidence and the refracting ray increases. As the angle of the prism is increased, the angle of deviation also increases. When white light is incident on one face of the prism, the light is split into 7 rays. Each ray is a separate color. The rays are violet, indigo, blue, green, yellow, orange and red. Each of these colors share the same frequency but different wavelengths. Violet has the least angle of refraction and therefore the highest refractive index and the shortest wavelength, whereas red has the greatest angle of refraction and therefore the least refractive index and the longest wavelength. Thus, violet has the greatest deviation and red the least deviation. When you look at a coin at the bottom of a tank of water, you feel as though the coin is closer to the surface than it really is. The ray has to be traced from the coin to the eye. So the ray passes from the denser water to the rarer air. So we can expect the angle of refraction to be greater than the angle of incidence. If the angle of refraction is traced back into the water, we find the apparent position of the coin as the intersection of the angle of refraction and the vertical line from the original coin position. A pencil looks bent in water due to the refraction of light in water. Try dragging the eye to different positions to see how the rays bend on contact with air before reaching the eye. When a ray of light from a denser medium enters a rarer medium, it refracts such that the angle of refraction is greater than the angle of incidence. Now, if you keep increasing the angle of incidence, you will reach a stage where the angle of refraction will be 90 degrees. The angle of incidence for which the angle of refraction is 90 degrees is known as the critical angle. If you now increase the angle of incidence, the ray does not refract out, but instead reflects back into the denser medium. This phenomena is called total internal reflection. For the water-air interface, the critical angle is 48.6 degrees. For angles above the critical angle, total internal reflection will take place. In a right-angled prism, the phenomena of total internal reflection can be observed by changing the angle of incidence, such that the angle R2 is greater than 42, which is the critical angle for a glass-air interface. When R2 is less than 42, the ray emerges out of the face R2 strikes at. When R2 is equal to 42, the ray emerges along the face. And when R2 is greater than 42, it does not emerge out from that face and reflects back into the prism. Any ray of light which when extended would pass through the focus emerges parallel to the principal axis in a concave lens. The angle that the ray makes does not matter, as long as its extension would pass through the focus. If a ray passes parallel to the principal axis of a concave lens and strikes the concave lens, it will deviate along a line from the focus. A ray incident at the pole of a concave lens will continue without any deviation. Drag the candle along the principal axis and place it at different positions to take a look at where the image forms. The concave lens produces virtual upright images which are diminished, no matter where the candle is placed. Any ray of light passing through the focus of a convex lens emerges out parallel to the principal axis. A ray of light passing parallel to the principal axis of a convex lens emerges through the focus. A ray incident at the pole of a convex lens will continue without any deviation. Drag the candle along the principal axis to check out where the image will form. It is interesting that the convex lens can produce real diminished images, which are inverted, as well as virtual magnified images which are upright. Myopia or short-sightedness is a disorder of the eye, wherein the convex lens of the eye forms an image which falls short of the retina and hence appears blurred. To correct this problem, a concave lens is used as glasses, which diverge the rays before they fall on the convex lens of the eye. Now the image falls on the retina and is clear. Hyperopia or long-sightedness is a disorder of the eye, wherein the convex lens of the eye forms an image which falls beyond the retina and hence appears blurred. To correct this problem, a convex lens is used as glasses, which converge the rays before they fall on the convex lens of the eye. Now the image falls on the retina and is clear. Myopia or short-sightedness is a disorder of the eye, wherein the convex lens of the eye forms an image which falls short of the retina and hence appears blurred. To correct this problem, a concave lens is used as glasses, which diverge the rays before they fall on the convex lens of the eye. Now the image falls on the retina and is clear.